All right, so today what we're going to do is section 4E. We're going to talk about geometric sequences. And geometric sequences are based not on arithmetic, but they're based on multiplication. Actually, what we'll be talking about is powers or exponents or indices, whichever word you like. So, when we're talking about a geometric sequence, the next number in the sequence is found by multiplication. So not addition or subtraction. Now, you could put division here, but in reality, division is simply multiplying by a number smaller than 1, right? So, multiplication or division, but we always define these using multiplication. So if you're dividing by 2, what is the same as divide by 2 as a multiplication? Multiply by half, exactly. So we still define it as multiplication. However, the multiplier that we use is defined in terms of division. It's defined as a ratio. So we're looking for what's called the common ratio. And ratio is what happens when you write it as a fraction. In other words, you write it as division. So it's a little confusing when you're talking about the terminology, but it's no big deal. So our first step in finding any geometric sequence is to find the common ratio. Now, again, a ratio means a fraction, but every number can be written as a fraction. For example, 2 is a fraction. It's 2 over 1. So you're still dealing with ratios. The reason why they have it as a ratio is because you could be multiplying by a number smaller than 1. So 1/2 is a ratio. We typically use it in its decimal form of 0.5. It makes no difference which one you prefer, the fraction or the decimal, because your calculator will do all the math for you. The only time it can become a problem when you want to use a fraction is if you have something where the fraction, if you change it from a fraction to a decimal, you would get a repeating decimal, which is not good for us because then we'd have to round and estimate. Okay? Once you've found the common ratio, and we're going to do that exactly the way we did in finding the common difference, what number multiplied times the first number would give you the second number, right? So same idea. And you need to test a few numbers just to make sure. Now these can get really bad really fast if the numbers are large. So your most common ones are 2, 0.5, okay, something like that. You could have 1/3. What does multiplying by 1/3 mean to do? To divide by 3. Excellent. So think about those equivalences here, because we're multiplying by 1/3 would mean divide by 3. It's very rare that you would get anything bigger than a 3. Very rare. And most of the time, it's going to be a 2. Because we're talking about exponents here. And what happens when exponents start getting big? The numbers start getting really big really fast. Okay? So most of the time, it's going to be a 2. But it could be a 0.5 and the fractional equivalent to that, of course, is 1/2. All right? So even though it's called a ratio, most of the time we're thinking about multiplication. Now, once we have that, remember that we're just going to have our first term. And do you remember the general form for first term? T what? The first term would be T to T1, yeah? And we also have another letter that we use when we're working with a formula. Right, we call it A. Okay? Then every other term is t sub n, right? That's any term. Don't put every other term, but any term, because it could be the first term. And then every other term is given, or the next term, let's put it that way. The next term, I keep changing my mind, don't I, is always t to the n plus 1.
What's the second one? Is it any term is t?
So any term is t to the n, t sub n. The next term is always t to the n plus 1. So we've talked about that terminology. Now, with geometric sequences, for some reason, though, they feel perfectly comfortable doing this, changing your letter on you. You don't have to worry about it. It's just some letter with a subscript at the end. It doesn't really matter what letter it is, but many, many times they may change it to V. Usually, V is typical, but it could be any other letter, right? Don't let that throw you. Now, there's a test for you to determine if indeed you are using the right ratio and if indeed something is a geometric sequence. And that is simply by taking your t to the n plus 1 and dividing it by t to the n. So in other words, if I take the third term and divide it by the one before it, so if the third term divided by the second term, and that should equal your common ratio. So you can always test to see if it's a geometric sequence by dividing those two. Now, I'm not sure if they're ever going to ask you to do that, but it's there for you and you can always test. And we'll look at some of the sample questions. Again, we'll do revision and be able to make these work, okay? All right. So to find any sequence, to find any number in a sequence, it's simply any number in the sequence equals the first one. The first one always just equals, let's do that one first. The first one is always just equal to A. But anyone after that is going to be equal to whatever term number you have times your common ratio. And the common ratio here is called R. Okay. So we're going to talk about how to work these in just a moment. So let's just go to the book so you can see some of these. So here we go. We have some geometric sequences. You'll see the first one they give you, 1, 2, 4, etc. To turn a 1 into a 2, we multiply it by 2. To turn a 2 into a 4, we multiply it by 2. To turn a 4 into an 8, we multiply it by 2. So you can see the sequence. You're just multiplying this time instead of adding. Okay? Now, not all sequences go up. If it goes up, it's called geometric. Anybody? Growth. Remember that? Do you remember that, Jim? So growth is if it's going up. Yeah? They could also be going down, which would be called geometric decay. There you go. Good. Okay? So, let's look at this next one. To go from 40 to 20, we divided it in half, right? So we either multiplied by 0.5 or you could say multiply by 1/2. Those are equivalent answers. It makes literally no difference which one you use, right? If you want to use the decimal there, that's fine. Then half of 20 is 10. So you see what's happening? And you can always test by taking, so if I'm here, here's term 3 divided by term 2. If you divide those, you get your common ratio. So you can always test by dividing one term by the previous term. Okay? Same thing in the earlier one. If we had 8 divided by 4, that gave us our common ratio of 2. Shh. All right. So, common ratio is just your multiplier. It can be a fraction, can be a decimal, can be a whole number. If it's a whole number, that means the numbers will be getting what? Bigger. If it's a fraction or a decimal, that means the numbers will be getting smaller. Okay? Now, you can have negatives, but not right now. All right? So if your question is, can it be negative? Yes, indeed, it can be, but not right now. It's going to do some weird things to your graph, so don't worry about it. Okay? All right. Now, so once you've found the common ratio, then you can generate any term. So here they're just talking about that. If you divide the third one by the second one, you should always get your common ratio. It always works. So make sure that you know that little test just in case if you're nervous about them. Now again, here you go. They've changed to V's. Doesn't make the slightest bit of difference. And what we're going to do is we're going to talk about graphing a geometric sequence. In order to graph a geometric sequence, we simply need to know the n. N just means what number term we're dealing with. And then, sorry, let me scroll up a little bit more. We're going to have to know our n, and then we know the value of that. And again, they're calling that v to the n. You could call it t to the n. That's what we called the other ones. Makes no difference. And you're going to get a series of ordered pairs, just like we did with the arithmetic sequence. Now, the difference here is that in geometric growth or geometric decay, the graph is going to be the exponential curve. Do you remember what happens with the exponential curve? It starts off looking kind of flat, and then it starts going up, and it goes up infinitely, right? This geometric decay, it starts off at the top, and then it gets smaller in that same pattern. Okay? So when you find these, the dots are not going to line up. So what the graph of a geometric sequence is an exponential curve. And remember, the exponential curve looks like half of a parabola. What's a graph of a parabola is the graph of a quadratic. That's a square. So the exponential curve, it looks like half of it, right? Now, again, you could have growth, which means that it'll be going up, or you can have decay, which means it'll be going down. Okay? Getting smaller and smaller and smaller, infinitely smaller. Okay? So you'll be taking some of those and you'll be graphing them. You must know those terms about growth and decay, because when you're asked a question about it, when you're doing the applications of these, say for example, a certain group of students was sent to extra tutoring in mathematics. There was a pattern in the improvement of their scores, and that was given as exponential growth, or it could be an arithmetic one as well. And you need to describe that as growth. Or we were trying to control a certain weed in a pond by doing different interventions, and they had different curves, different decays. We want the one with the fastest amount of decay, right, to be able to get rid of the weed as quickly as possible. So you're going to be given those applications, so you need to use those words, growth and decay. Right? So there's you see a graph. Here you'll see this one is a graph of decay. Sorry, let me scroll up just a bit further. This one is a graph of decay because it starts high and then goes closer and closer and closer to 0, but never quite gets there. Right? Infinitely smaller. Okay? All right. So you're going to have to graph some geometric sequences as well. Okay? So your two tasks in this section are to simply find the next number in the sequence, and you do that by simply multiplying the term number by whatever your R is. All right? And then, guys, you're going to have to graph some.